Hello everyone and welcome back to our channel MooTechie. A special welcome to all the dairy technologists and students joining us. This is the fourth class in our Unit 2 series on mechanical separation. In our last session, we explored clarifiers. Today we will focus on another essential centrifugal machine, the cream separator. We are now moving on to the topic of the cream separator. This is a machine that separates cream and skim milk from whole milk by means of centrifugal force. The inventor of the first continuously working centrifugal separator, which made modern cream separation possible, was Gustaf de Laval. Cream separators come in several types. They can be hand-operated or power-driven. Based on their design and how they handle the product, they are classified as open-bowl separators, semi-closed separators, hermetic separators, and self-desludging separators. Let's start with the open-bowl separator. This type of separator is open to the atmosphere. It has an open top for the milk inlet. The outlets for both cream and skim milk are at atmospheric pressure, meaning they are not pressurized. A significant disadvantage of this design is that it causes a lot of excess foaming in the skim milk. This slide provides a parts list for an open bowl separator. Key components include the milk tank, the tank tap handle, the float chamber, the float, the cream spout, the skimmed milk spout, the bowl assembly, the main body, and the electric motor. The construction of an open bowl separator includes a supply can or milk tank, a milk faucet, and a regulating chamber with a float to control flow. It has a cream screw and a skim milk screw to adjust the outputs, which exit through a cream spout and a skim milk spout. The heart of the machine is the separator bowl or disc stack, which consists of the bowl shell, milk distributor, discs, and a rubber ring. Other important parts are the spindle, gears, a crank handle for manual operation, a bowl nut, an electrical motor, a centrifugal pump, a worm and worm wheel gear system, and the bowl spindle. The disc stack itself is made up of several precise components. These include the coupling nut, discharge ring, small bowl ring, coupling ring, bowl top, large bowl ring, and the top disc. Other parts are the bowl shell, the tubular shaft, the distributor, the intermediate top disc, the intermediate discs, and the bottom disc. The worm and worm wheel mechanism is a type of gear system that transfers power from the motor to the bowl spindle, causing the bowl to rotate at high speed. The specifications for an open bowl separator are impressive. They can have around 120 discs, which determines their capacity. The discs have an angle of inclination between 45 and 60 degrees. The outward diameters of these discs range from 200 to 300 millimeters, and they are very thin, with a wall thickness of about 0.4 millimeters. The bowl rotates at high speeds between 5,500 and 6,000 rpm, and it can handle a mass flow rate of up to 20,000 liters per hour. This slide shows an image of an open bowl separator. Here is another image of the equipment. The operation of an open bowl separator requires some adjustments. To obtain high-fat cream, the space between the discs must be increased. The machine can experience clogging if the fat content in the cream rises above 55 to 60%. If the milk temperature is below 25 degrees Celsius, the higher viscosity requires the distance between the discs to be increased. The cream screw is used to manipulate the flow rate of the cream exiting the machine. The cream screw is a critical control. Turning the screw in makes the cream thicker, while driving it out results in thinner cream. If the screw is driven all the way against the stop, no cream will come out at all. This screw regulates the ratio of skim milk to cream. It should be adjusted so the fat content in the cream is about 33%. If the cream is too thin, meaning the fat content is too low, it reduces the amount of skim milk available for other uses and increases the volume of cream that must be handled. Low-fat cream is also more difficult to churn into butter efficiently. There are several disadvantages to the open bowl design. It is only suited for small capacities. Because the discharge is to atmospheric pressure, the product is open to atmospheric contamination and ingress of air, which makes the product foamy. Furthermore, it cannot be directly linked to a pasteurizer, so separation cannot be done at the optimum temperature of 40 to 45 degrees Celsius. Next, we have the semi-closed separator. In this design, milk still enters at atmospheric pressure, but it uses a special outlet device called pairing discs. These are pairing discs, separators. The pairing discs prevent aeration of the product, but they must be sufficiently covered with liquid to function properly. A pairing disc maintains a constant operating liquid level under the bowl. The rims of the stationary pairing discs dip into the rotating columns of liquid, continuously pairing out a certain amount. This creates a pumping effect that neutralizes the static pressure from the milk supply. The kinetic energy of the rotating liquid is converted into pressure within the pairing disc, and this pressure is always equal to the pressure drop in the downstream pipeline. This is a labeled diagram of a semi-closed separator. It shows the full cream milk inlet A, skim milk outlet B, and cream outlet C. Key parts include the inlet vessel, 1. The skim milk screw with a pressure gauge, 2. The cream screw with a cream flow meter, 3. The bowl with disc assembly, 4. The cover, 5. The frame, 6. The bowl spindle, 7. Shaft bearings, 8 and 9. The bowl arresting screw, 11. And a revolution indicator, 12. Here is how a semi-closed separator works. The milk enters the ribbed distributor and is accelerated to the speed of the rotating bowl before it continues into the separation channels in the disc stack. The cream, being lighter, moves inwards towards the axis of rotation and passes through channels to the cream pairing chamber. The skim milk, being heavier, leaves the disc stack at the outer edge and passes between the top disc and the bowl hood to the skim milk pairing chamber. This slide shows a diagram illustrating the liquid flow and the action of the pairing discs. Now let's look at the Hermetic separator. In this advanced design, milk is supplied to the bowl directly through the hollow bowl spindle. The bowl is completely filled with milk during operation, leaving no air in the center. The pressure generated by an external product pump is sufficient to overcome the flow resistance through the separator all the way to the discharge pumps at the outlets for cream and skim milk. This design is used for self-desludging separators and can be included in a clean-in-place or CIP circuit. This slide shows the Hermetic inlet seals that prevent air from entering the system. The hollow spindle is a key feature, allowing milk to be fed into the sealed bowl. This is an image of the bowl assembly. Here we see the Hermetic outlet seals that maintain pressure and prevent air ingress at the product discharge points. This slide shows the product discharge area. Another image of the Hermetic separator. Finally, we have the self-desludging separator. This type includes a mechanism for automatically removing solid sediment without having to stop the machine. The sediment discharge sequence can be triggered automatically by a preset timer, by a sensor in the process line, or manually by an operator pushing a button. The discharge system works hydraulically. A fixed volume of water is added to initiate the drainage of the balance water that holds the bowl closed. When this water drains from the space below the sliding bowl bottom, the bottom drops instantly, and the accumulated sediment is ejected out of discharge ports at the periphery of the bowl. New balance water is then automatically supplied from the service system to close the bowl again. This water moves the sliding bowl bottom upwards to tighten against the seal ring. This entire sediment discharge process happens in just a few tenths of a second. The diagram shows the sliding bowl bottom and the sediment discharge port. This diagram illustrates the self-desludging mechanism in 3 stages. A. Showing sediment accumulation. B. The valve opening and water release. And C. The solid ejection phase. The final slide shows a simple diagram of the feed entering and the liquid discharge leaving the separator. Thank you for joining this comprehensive class on cream separators. We covered the evolution from simple open bowl designs to sophisticated hermetic and self-cleaning machines. Understanding these different separators is crucial for efficiently producing cream, skim milk, and ensuring the overall quality of dairy products. Thank you. See you in the next class.